right, statisticians, welcome back. Hope everyone's doing all right. We are now getting into the beginning of our final giant concept of testing. So today we are going to start with the basics of hypothesis testing. So we're starting off with this scenario and determine, is this gender discrimination? So a local engineering firm had to conduct a series of layoffs recently. They laid off 10 people. The company has 180 employees. All are equally qualified, so the company decides to use a lottery system to be carried out by the manager to decide who will be laid off. The manager posts a list of employees to be laid off. 5 women and 5 men are laid off. One of the women claims it's gender discrimination and starts a lawsuit against the company. The manager responds, how could there be gender discrimination when half the employees laid off were female, half were male? What additional information do you need to evaluate this statement? So some additional information that we might need, I'll let you think about it. Well, we probably need to know what the breakdown is of men and women in the company. So we need to know, I don't know why that is bold there, or that's highlighted, but sure, why not? How many males, females work at the company? And come to find out of 180 total, there are 60 women and 120 men. So there are twice as many men as women, or we can say that the probability of women, the proportion of women is 1 out of 3, or 0.333333333333. So we're going to investigate the gender discrimination claim. How could we do that? There's a lot of different ways we can simulate this. So you might think maybe we can use dice. Maybe 1 and 2 are women and 3 to 6 are men. That would give us a 1/3 being women and 2/3 being men. Maybe we can use a spinner where 1/3 are women and 2/3 are men. Or maybe we use a random number generator, RNG. We can set 1 to 60 are women and 61 to 180 are men. Or even simpler, just do 1s, 2s, or 3s, where 1 is women and 2 and 3 are men. So that is what I did. I went to random.org. I requested 20 sets with 10 unique random integers in each, taken from 1 to 180. And there was no repeats in here. So basically what I did was I was like, all right, I counted up how many of the numbers were between 1 and 60, and that was how many women I had. So for example, here I had 5 women out of a total of 10, and I counted that up and I turned that into a decimal. So then I went to Statlet.com, hello me, and there that 5 women out of 10 was, that would be 0.5 or 50%. I counted that up for all 20 of my sets, and I got 20 data points here, and you can see them all here. We got a couple 0.1s, a few 0.4s, more 0.3s, the most 0.4s, but still a couple 0.5. So I did this 20 times, 19 times. Apparently I skipped one, so 19 times. And out of that 19 times, I got 2 of them that were 0.5. That's hilarious. I must have missed one of them. So I'm going to copy that over. I don't know how to copy it over. Let me see. Control, Shift, Window, I think. Hopefully you can hear my girl dog trying to dig through the couch behind me. So before we copy and paste that, let's talk a little bit about hypotheses. So you guys have seen hypotheses in science, hopefully. We have 2 here. So we're going to have our null hypothesis is basically what we're testing here. So our null hypothesis, we're going to call that H. And then we want a little subscript here. Remember, we can do subscript on Cami pretty easily. H sub 0. I'm going to click subscript to get out of subscript. And our null hypothesis, I need to get back out of it. Our null hypothesis, in this case, we're going to be talking about proportion. So I want to test and see if that proportion is 1/3 or that 0.3 repeating. And then on the contrast, alternative. Yeah, I did it right. Our alternative hypothesis is going to be H sub A. Hopefully you didn't see that craziness happening. Let me find where my subscript is. That'd be nice if I could have a subscript here. How about text box and there subscript H sub A? That sounds like I can cut out some things. So alternative hypothesis, H sub A, let's get a subscript A, is going to be, well, they think that there's too many women being selected. So they're going to say that the proportion of women is being selected to, be let go is going to be greater than that 1/3 or that 0.3 repeating. Let me get rid of that 0.3. Let's just get some fractions here. So we're thinking that these women are saying that, hey, this is probably greater than that. So we look at our graph here. I think we can go paste that over now. And we see that 2 out of 19. So we see, let's get a little drawing tool here. We see that 2 out of 19 end up being more than 50% or more. So that is kind of what we're thinking there. So we're saying, all right, that's not very uncommon to have that there. And so we're going to say what percentage of that, there we go. So that number 4 there says what percentage of the dots represent half or more of the females being laid off. And that's going to be everything to 50% or more there. And so we have that as 2 out of 19, which when we throw that into our trusty phone calculator, 2 out of 19 gives us just over 10%, so 0.105, so 10.5%. So what does that tell us? That tells us that, assuming the lottery to see who got fired was carried out fairly, there is a 10.5% probability of getting a sample proportion of 0.5 or higher. So do we have convincing evidence of gender discrimination? And we can say no, a sample proportion of 0.5 or higher happened fairly often. I know 2 out of 19 might not seem fairly often, but if we're doing that 100 times, it's going to happen 10 or so times out of the 100. And remember, we often compare our that probabilities, which we saw in our Parkinson's idea, is that our p-value, we often compare that to 5%. So this is greater than 5%. We've been talking about that magic 5% for a long, long time now. So this is a little above 5%. So let's jot down some of the basics on the next page. We have, let me scroll over so I got some more room here. Nice big box here. I don't know how to get rid of this, so I'm just going to keep rolling with it. We have our null hypothesis, H sub 0. And so that's either going to be of our, remember we have mean, or our proportion. And that's going to equal our null value. The alternative hypothesis is going to be H sub A. Let's scroll down so you can see that a little bit. H sub A. Again, we're going to have mean or proportion there for P. This is going to be less than or greater than or not equal to. Whoa, I don't know what that did. Come back. Or not. I can caps lock. Oh my goodness. Turn caps lock off. Or not equal to. Let me draw a little line through that. Let me I can't draw a line through not equal to. Fantastic. Good job, text box. Not equal to, how about we try and unhighlight this? Go away, me. Clear. Background, clear. There we go. There we go, not equal to, and we're gonna have that same value as well. So we kind of saw that up here with P equal to 1/3 and P is greater than 1/3. Maybe we're using 1/2 there or 0.5 there. The world really doesn't know. But notice how they're both the 1/3. So we're saying, hey, we're thinking it should be close to 1/3, but you know, for gender discrimination, the probability is going to be above 1/3. And like, hey, this 50% just happened. How often should we be expecting to see that 50%? And it looks like it only should happen 2 out of 19 times, or approximately 10% of the time, which is kind of a lot of times there. So our hypotheses, we have our null hypothesis, H sub 0, our alternative hypothesis, H sub A. And we're going to have mean. Remember, our variable for mean is not M. It is instead the letter mu. So let's make that much bigger for you. We have our mean is mu. Oh, that's me. Come on, mu. For our population mean. Next, we want to talk a little bit about p-value. We chatted a little bit about this in the Parkinson's idea. The probability of getting the results, or more extreme, either higher or lower, purely by chance if the null is true. So we were trying to see what the p-value was of getting that 50% or above if it actually was 1/3 women and 2/3 men. And then finally, we will make a conclusion based on that p-value, normally compared to about 5%. That 5% is going to be a significance level that we're going to talk about real quick. So our conclusions, we either do or we do not have convincing evidence against the null hypothesis. So we're going to compare it to the significance level. This is going to be a Greek letter that I'm about to fill in. And if that p-value is smaller than that significance level, then it is significant evidence. And that's staying right there. So let's talk about what that significance level. That significance level is normally 5%. Can use other values as well. Let's see if we can go find it. There it is. It is alpha. So nice Greek letter that you should recognize. That is alpha. We want to move you over. This is fun. Sorry for how often I'm doing this. Copy. We want to make another one of them. Nice and big. So we're going to compare this, kind of like how we have been doing, to our p-value. Now we're going to start running these tests and actually calculating p-values and getting those and comparing them to our alpha significance level, generally of 5% or maybe 10%, maybe lower, maybe higher. So sorry for the 15-minute video, but I want you to now try to check your understanding. Submit this when you're done. Email your teacher if you got any questions.